Welcome you all to the second lecture. So, if you recall in the last lecture we started with an optimization problem of the following form. So, we are going to minimize f of x subject to the condition that x is in some constraint set S. Okay. And we also discussed about the solution concepts. One is the global solution and the other is the local solution. To give a 1-minute recap of the examples. So, if you have so yeah, let us consider S to be R. Okay. So, the let S equal to the real line, okay. And if so, if f of x equal to x, okay. So, no global local solutions, yeah, neither a global solution nor a local solution. So, if f of x equals x minus 1 into x plus 1, then no global solution, but a local solution at x equal to 0.5, okay. And if f of x equal to x squared, then a unique local solution at x equal to 0. This is also a global solution. Okay, I will write it as x star to clarify. Okay. And if f of x equals x minus 2 into x minus 1 into x plus 2. Okay. So, we have a local solution at x star equal to, yeah. So, when I write x minus 2, yeah. So, there is a local solution at 1.5, okay, and a global solution which is different from this, a global solution at some x star in the interval minus 2 comma 0. Okay. So, I mean this can be precisely found by solving this quadratic equation. Okay. So, you can actually see that given a function f of x, you can have a global solution or a local solution, or you may not have a global solution or a local solution. Even if you have both local solution and a global solution, okay, it could turn out that there could be local solutions which are not the global solutions, isn't it. So, now we actually ask two questions. One is regarding the existence of a global solution or a local solution, right. So, that is, given a problem, how do I find whether there exists a global solution or not. Okay. So, that is one question. Okay. The other question is when can I say that a local solution is a global solution as well. Okay. So, these are two very important questions, and it has been answered many years back. Okay. So, the first question was answered by Weierstrass. Okay. So, and it is famously called as the Weierstrass theorem. And what does it say? It says that consider f to be a continuous function and So, the objective function needs to be continuous and the constraint set S be non-empty, closed and bounded. Okay. If all of these conditions are satisfied, then there exists a global solution x star such that f of x star is less than or equal to f of y for all y in S. Okay. So, this is called as the Weierstrass theorem. So, what this says is very simple, it says that the function f needs to be continuous, okay, and the constraint set has to be a non-empty set, it has to be a closed set and a bounded set. Okay. So, if all of these happens, then there will certainly exist a global solution. Okay. So, we have actually assumed initially that f will be a twice differentiable function, right. So, it is certainly continuous, we know that, and yeah, we have also assumed that the continuity of the function is not a problem in all the examples that we have given here. Okay. But if you see here, you can see that the constraint set S is actually the real line itself. So, it is certainly non-empty, it is certainly closed, but it is not bounded, right. So, it is neither bounded on the left nor bounded on the right, is not it. So, since the condition of boundedness is violated, that is the reason why we actually have examples where there is no global solution. Okay. I mean, yeah, this actually gives a sufficient condition for the optimization problem to be to admit a global solution. Okay. And so, let us now answer the next question, when does it happen that the local minimum turns out to be a global minimum, right. So, yeah, there again we have a theorem. Let f be a convex function, the objective function which we are minimizing is assumed to be a convex function, and let the constraint set S be a convex set. Then the local solution x star is also a global solution Okay. So, maybe I will spend a few minutes explaining what is a convex set and a convex function. Okay. So, because we have used these terminologies here, that a set being a convex set and a function being a convex function, right. So, when is a set called a convex set? Okay. So, practically speaking, okay, a convex set is a set when, maybe I will write down the definition and then explain the physical meaning. Okay. So, a set X is convex if x y in X implies lambda x plus 1 minus lambda y in X for all lambda in 0 1. Okay. So, to explain what this is, so consider that we have the following set. Okay, so it is a circle, not drawn very well, but I suppose you understand, and the set X is all points within this circle and also on the boundary. Okay. So, I claim that this set is a convex set. Why is that so? Take any 2 points on this set, say for example this point and this point, okay, and draw a line in between them. So, all points on this line, okay, on this line segment is within the set, right. So, this set is actually a convex set, okay, and that is exactly what this definition says. So, take any 2 points. So, let us say this is the point x and this is the point y, okay. So, when you take any 2 points on this set x comma y in capital X, then lambda x plus 1 minus lambda into y actually represents the points on the line segment joining x comma y, okay. So, you can see that when you put lambda equal to 0, you get the point y, and when you put lambda equal to 1, you get the point x, and yeah. So, if you put anything in between, let us say lambda equal to half, right. So, you get the midpoint x plus y by 2, and similarly you can get all the other points if you put the appropriate values of lambda, okay. So, yeah, this is an example for a convex set, and what is an example for a non-convex set? So, let us say I have this kidney shaped set where I have all the points on the boundary as well as the interior of the kidney, okay. Now, this is not a convex set, because if I join these 2 points, say this is a point on the set and this is another point on the set, okay. So, if I join these 2 points, the line segment in between does not lie within the set, okay. So, if that is the case, then such a set is a non-convex set. This is a non-convex set and this is a convex set, okay. So, that is the definition of a convex set, okay. Now, what is the definition of a convex function? Okay. So, consider a function f from x to r where x is a convex set, then f is a convex function if f of lambda x plus 1 minus lambda y is less than or equal to lambda f of x plus 1 minus lambda f of y for all x y in x for all lambda in 0 comma 1. Okay, so, this is the definition for a convex function. Okay. So, yeah, what is the physical meaning of whatever I have written here? So, consider this particular function, okay, and consider 2 points x and y, okay, and join them. If this line segment lies above the curve, then the function is a convex function, okay, and this should happen for any x and y that you take. Okay. So, what I have drawn here is a convex function. So, you can take any 2 points and the line segment joining them would be lying above the curve, right. So, what this says is that the right hand side here is the line segment joining f of x and f of y, and the left hand side here is the function value at that particular point. So, you can see that the function value is less than or equal to the line segment that joins the points x and y. Okay. So, when this happens for any xy in the domain of f, then we call such a function as a convex function. Okay. So, if the exact reverse inequality holds, then such a function is called as a concave function. Okay. So, yeah, if it turns out that if f of lambda x plus 1 minus lambda y is greater than or equal to lambda f of x plus 1 minus lambda f of y for all x y in x for all lambda in 0 1, then f is a concave function. So, yeah, if you consider the inverted curve of what I have drawn here, something like this, then you can see that the curve always lies above the line segment, or the line segment lies below the curve, right. So, in such a case it is called as a concave function. Okay. So, yeah, we could have functions which are neither convex nor concave, right. So, in certain parts it is convex and in certain parts it is concave, right. So, for example, you can have functions like right. So, you can see that in this part up till here it is concave. So, here it is concave, and in this part it is convex, right. So, you could have functions of this sort as well. And now, let us come back to the theorem. Okay. What does this say? It says that if f is a convex function and the constraint is a convex set, then the local solution x star is also a global solution, right. So, let us check which of these functions is actually a convex function. Okay. So, f of x equal to x is actually a convex function. Okay. Yeah. So, another way of verifying whether a function is convex function is yeah, I mean that actually involves finding the Hessian matrix. Okay. So, or yeah, if it is domain of f is a subset of R, then in that case yeah, you can do it with the second order derivative. Okay. So, maybe I will indicate that as well. So, suppose that f is twice differentiable. Okay. Then f is convex if and only if the Hessian matrix is positive semi definite for all x in the domain of x. Okay. Okay. So, to give you an idea of what is positive definite. Okay. So, as a on a side note, so we will write that, I mean the Hessian matrix is just the second, I mean the matrix consisting of the second order derivatives of f. Okay. So, it is just dou squared f by dou x1 squared, dou squared f by dou x1 dou x2 dot 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 dou squared f by dou x1 dou xn, dou squared f by dou x2 dou x1, dou squared f by dou x2 dou xn dot 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 dou squared f by dou x1 dou xn dou x1, dou squared f by dou xn dou x2 dot 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 dou squared f by dou xn squared. Okay. So, yeah, this is the Hessian matrix, and you can see that it is an n cross n matrix. Okay. So, we call this positive semi definite if the following condition is satisfied. Okay. So, you take any t, a vector, an n length vector. Okay. So, and you compute T transpose into the Hessian matrix into T. Okay. So, T is for any T which is an n dimensional vector. So, you should have this. Okay. So, if this condition is satisfied, then we say that del 2 f of x is actually positive semi definite. Okay. So, yeah, this notation that you have here denotes the denotes that this matrix what you have here is positive semi definite. Okay. So, yeah, if we check this condition, okay, yeah, we can verify whether f is a convex function or not. If this constraint, I mean, if this condition is satisfied, then f is a convex function, otherwise it is not. Okay. All right. So, yeah, now coming back to the examples here. Okay. So, you can see that when f of x equal to x, we have f double dash of x equal to 0. Okay. So, that is convex of course, but it does not have a local solution at all, right. So, yeah, there is no question of asking whether the local solution is a global solution or not. Okay. So, now when you take the example f of x equal to x minus 1 into x plus 1. Okay. So, I say I have mentioned that there is a local solution at x star, but it is not a global solution. Okay. So, that means that this function may not be convex. So, if we check what is f double dash of x, it is actually, so this is x squared minus 1 into x, that is x cube minus x. So, f double dash is, okay, so the differential of 3x squared minus 1, which is 6x, okay, but this is positive when x is positive, but negative when x is negative, right. So, yeah, this is, as you can see, is not a convex function. Okay. So, yeah, it implies that this is not a convex function, and thus you actually have a local solution which is not a global solution. Okay. Yes. And the next you have f of x. So, if you consider the problem f of x is equal to x squared. Okay. So, here you can clearly see that f double dash of x is actually equal to 2x, sorry 2, and this is greater than 0 always, and so this is a convex function. Since this is a convex function defined on a convex set, so the real line is also a convex set, right. So, you can take any 2 points, and when you join the line in between 2 points, right. So, it lies within the set. So, this is a convex set, no issues with that. S is equal to R is actually a convex set. So, f of x equal to x squared is a convex function. So, you can see that every local solution in this setting is also a global solution, and yeah, the final example, you can see that Yeah, so we will now find if this function, the quartic function that we have at the end, is a convex function or not. Okay. So it can be written as, so f dash of x is d by dx of x power 4 minus 5x squared plus 4x. Okay. So you can find this out, not difficult. So this is 4x cube minus 10x plus 4, and f double dash of x is 12x squared minus 10, and this is less than 0 if mod x is less than or equal to root 5 by 6. Okay. So you can see that this is again not a convex function, not a convex function. Okay. So coming back to the theorem, you can see that if it turned out that f were a convex function and the constraint set is a convex set, then the local solution of x star of the optimization problem is also a global solution. Okay. So in the next class we will look at given an optimization problem, how to find a local solution or a global solution, what are the characteristics of a global solution or a local solution for both a constrained optimization problem as well as an unconstrained optimization problem. Thank you.